In the previous video, we proved that Gauss's method works as a method for computing the value of Legendre symbols, and in this video, we will actually work through a bunch of examples of doing it. So let's just do a brief overview of how Gauss's method works. We're going to compute values of Legendre symbols a over p. P is an odd prime, and a is relatively prime to p. First, compute phi of p over 2. P is a prime, so phi of p is just p minus 1. P minus 1 over 2 is a value that pops up a few times, so it's nice to just have it written down somewhere. Optionally, but very convenient, if a is negative or larger than p, replace a with the remainder under division by p. Quadratic residues are all computed mod p, so it doesn't really matter if you do this. Replace something with an equivalent value mod p. And the smallest positive equivalent value is going to be the easiest thing to work with. So from this point forward, we're just going to assume we've done this. A is relatively prime to p, so it's not equivalent to 0 mod p. So it's in between 1 and p minus 1. It's not technically required to do this replacement, but it is very convenient. Next, list out the multiples, a times 2a, etc., up to p minus 1 over 2 times a. Now, since we're generating this list, what we're really doing to get from one to the next is adding a. Starting with a, add a, now you have 2a, add a, now you have 3a, and so forth. So we're just doing a bunch of steps of addition. If at any point you get something larger than p, what we want to do is then subtract p from the result. In other words, reduce all of these values modulo p to generate this list. Now what you look for in your list of remainders is how many of them are strictly larger than p minus 1 over 2. Count how many remainders you generated are bigger than p minus 1 over 2, and raise negative 1 to that power. Now, all you really care about, since we're raising negative 1 to a power, is was that quantity even or was it odd? If the quantity of remainders larger than p minus 1 over 2, n, is even, you get negative 1 to an even power, and therefore a is a quadratic residue mod p. If the quantity of large remainders is odd, then you get out a minus 1, and it's a quadratic non-residue mod p. So let's look through some examples. Determine whether 35 is a quadratic residue modulo 79 or not, and 79 is in fact an odd prime number. So phi of 79 over 2 is 39. So we compute 39 multiples of 35. 35 plus 35, we get 70. Now if I add 35, I get 105. But since I'm working modulo 79, I replace 105 with 26. Next, I add 35 and I get 61. If I add 35, I would get 96, but 96 modulo 79, I replace with 17. I add 35 and I get 52. I continue in this manner. I keep adding 35 over and over again. Whenever I pass the value of 79, I just subtract 79 so that I have easier computations, and I just keep adding. And I do this until I have 39 total items in the list. So from the beginning, plus 35 but minus 79, plus 35 but minus 79, plus 35 but minus 79, plus 35 plus 35 but minus 79, and so forth and so forth. Now in each row here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 total objects. And I'm trying to get a total of 39 of them. So if I generate 4 rows here, each has 9, so now I have 36 objects in my list, which means I need 3 more. So when I've done this procedure and I count out to make sure there's 39 total objects, here are all of my remainders. Notice something very nice happened. When I added 35 here, okay, 78 plus 35 is 103. 103 modulo 79 was 34. What we kind of saw was that by going forward 9 steps, the result was taking away 1. This works because 9 times 35 is equivalent to negative 1, mod 79. So adding 9 copies of 35 is equivalent to taking away 1. So since I made my rows have length 9, going down to the next row would be the same thing as going forward 9 steps in the procedure. So going forward 9 steps in the procedure, just take away 1. Going forward 9 steps, take away 1, take away 1, take away 1. So this was not a coincidence. You may have noticed this. that as these rows got listed out, this was just one less than that, this was one less than that, this was one less than that, and then this is actually one less than this. 32, 67, 23 goes to 31, 66, 22. This isn't because, I'm always going to list things out and then just start taking away one. This was specifically because we noticed that when I go to the next step here, I'm one less than a value I've already seen. So I made a very deliberate decision to arrange my rows to represent this subtraction by one procedure, and it helps make it easy to not make mistakes. But overall, in this list of remainders, I ask how many of them are larger than 39. If we count that up, I'm just looking for bigger than 39. One of them, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. There are 21 terms that are bigger than 39, and therefore the Legendre symbol 35 over 79 is -1 because there was an odd quantity. So 35 is not a quadratic residue modulo 79. All right, the first time working through it takes some explanation, but trust me, once you get used to it, this is actually quite fast. Let's look at another example. Determine whether 30 is a quadratic residue mod 101, and 101 is a prime number. So phi of 101 over 2 is 50. So we need 50 multiples of 30. So we make the first multiples of 30 and we reduce mod 101. Since I happen to know I want 50 total, I'm going to make rows of 10 and have 5 total rows. I like these geometric arrangements to make sure I get exactly the quantity of objects I want. So let's just keep adding 30. 30, 60, 90. 120, so take away 101. Plus 30, 49, 79, 109, take away 101, 8. Plus 30, plus 30, plus 30. Now when I add 30, I would get up to 128. If I take away 101, I get to 27. So if I'm making my rows be of length 10, I've observed that moving down one row subtracts 3. So adding 30 here would be equivalent to adding 30 here, take away 3, take away 3. So what I now know is that when I move down to the next row, I'm actually just taking away 3. 57, 87, 16, 46, 76, 5, etc., etc. Here's the next row, take away 3. Now here's the next row. Take away 3 at every step, but here 2 minus 3 would actually be -1, but I want my legitimate remainders. So -1 is actually the same thing as 100, and that does match adding 30 to 70. Take away 3, take away 3, take away 3, take away 3's again, and we're all fine. So now I have 5 rows with 10 each, so I have my 50 multiples of 30, all reduced mod 101. Count how many are larger than 50. Everything here is larger than 50, that's 4 of them, but not 48. Okay, each row I took away 3, so it's not surprising that eventually they weren't actually big anymore. All of these are bigger than 50, so that's another 5. None of those. All of these, so that's another 5. Just these 2, so there's 2. All of these were bigger than 50, and all of these were bigger than 50, so there's another 5 and 5. So 10 plus 10 plus 6, that's 26 such terms. With an even quantity, the Legendre symbol evaluates to -1 to an even number, that's 1. So 30 is a quadratic residue modulo 101. Okay, let's revisit an earlier example. Show that the Legendre symbol -1 by p is 1 if and only if p is equivalent to 1 mod 4. List out multiples of -1. That's actually pretty easy. -1 up to -p minus 1 over 2. But now to get the least positive values, we add p to each of them. So here's all of my remainders. These count at the biggest possible remainder and go down by 1 at every step. Okay, until we reach the last one. But the last one, p minus 1 over 2, is actually p plus 1 over 2. That's bigger than p minus 1 over 2. So every single remainder that we generated was a big one. Therefore, by Gauss's method now, -1 to the p is -1 to the p minus 1 over 2, and we've already seen that this exponent, p minus 1 over 2, is even if and only if p is equivalent to 1 mod 4. So the only way I get out an even exponent here is for p to be equivalent to 1 mod 4. Therefore, by Gauss's method, as well as by Euler's method, we already knew this result. The Legendre symbol negative 1 by p is 1 if and only if p is equivalent to 1 mod 4. And now let's look at a new example. Show that the Legendre symbol 2 by p is 1. In other words, 2 is a quadratic residue mod p, if and only if p is plus or minus 1 modulo 8. So list out all your multiples. Observe that last multiple is exactly p minus 1. So the multiples got bigger and bigger and bigger until they hit p minus 1, and then I stopped. So none of the multiples were actually p or larger. So I never needed to do any reduction mod p. The question, however, is how many of these multiples are actually strictly larger than p minus 1 over 2? If p is equivalent to 1 mod 4, then p minus 1 over 2 is an even number. And if it's an even number, then it's going to be in this list of multiples of 2. So if p is equivalent to 1 mod 4, this cutoff value is in the list. In which case, p is equivalent to 1 mod 4, so write it as a multiple of 4 plus 1. P minus 1 over 2 is 2k. So this is how many items are in the list, because I took multiples up to this quantity. So there are 2k items in the list. How many of them are less than or equal to p minus 1 over 2? But p minus 1 over 2 is exactly 2k. So everything up to 2k is exactly less than or equal to 2k. How many items in this list? This is 2 times 1, 2 times 2, all the way up to 2 times k. So k elements of the list were less than or equal to the cutoff, which means since there were 2k items total and k of them are small, then k of them are big. So if p is equivalent to 1 mod 4, in other words, p is 4k plus 1, by Gauss's method, the Legendre symbol 2 by p is negative 1 to the power how many remainders were big, and we determined k of them are big. But we care whether that exponent is even or odd. So this is 1 if and only if k is even. If k is even, I come back to p and I find that p is actually equivalent to 1 mod 8. So if p is equivalent to 1 mod 4, 2 is a quadratic residue if and only if p is equivalent to 1 mod 8. Of the things that are equivalent to 1 mod 4, what could they be equivalent to mod 8? Either 1 or 5. So if p is equivalent to 1 mod 8 or 5 mod 8, then p is equivalent to 1 mod 4, but only 1 mod 8 has 2 being a quadratic residue. So that's all primes equivalent to 1 mod 4. Okay. If p is equivalent to 1 mod 4, so what is p equivalent to mod 8? It could be 1, 3, 5, or 7. What's p equivalent to mod 4? If it's equivalent to 1 mod 8, it's equivalent to 1 mod 4. If it's equivalent to 3 mod 8, it's equivalent to 3 mod 4. If it's equivalent to 5 mod 8, it's equivalent to 1 mod 4, and 7 mod 8 would be 3 mod 4. And what we've determined is, of the rows in which p is equivalent to 1 mod 4, is 2 a quadratic residue. 2 is a quadratic residue here, but 2 is not a quadratic residue here. That's what we've determined so far. So now what we have to address is, what about the primes equivalent to 3 mod 4? So p in this case is 4k plus 3. So p minus 1 over 2 is an odd number. So therefore, this value can't be in the list of multiples. My multiples of 2 are all even. This is an odd number, so it's not in the list. So which multiples are less than or equal to p minus 1 over 2? Everything up to 2k is less than or equal to 2k plus 1. The next multiple of 2 would be 2k plus 2, which is bigger. So since there are this many terms in the list, k of them, 2 times 1, 2 times 2, up to 2 times k of them are small. So 2k plus 1 elements total, k of them small, therefore the remaining k plus 1 elements were big. So the Legendre symbol, by Gauss's method, is computed as negative 1 to the k plus 1. This is equal to 1 if and only if k is odd, because it's got this plus 1 in there. So k being odd means the exponent will be even. K is odd, I plug that back in here, and I would get, so if k is an odd number, and P is equal to 4K plus 3, we would end up with P is equal to 8J plus 7. So when P is equivalent to 3 mod 4, in other words, these two possibilities, 2 is a quadratic residue if and only if P is equivalent to 7 mod 8. So we come back here and we fill this in. When it's 7 mod 8, 2 is a quadratic residue, and when it's 3 mod 8, it's not. 7 mod 8 is the same thing as negative 1 mod 8. So now what we have determined is 2 is a quadratic residue exactly when P is equivalent to 1 or negative 1 mod 8, but not when it's 3 or 5 mod 8. So this is a handy thing to keep in mind. We're going to actually use this result in the future. Negative 1 is a quadratic residue if and only if P is equivalent to 1 mod 4. 2 is a quadratic residue mod P if and only if P is plus or minus 1 mod 8. These are now known results that we're going to rely on in the future.